Welcome back to The Explainer. Today, we are getting into something that is literally running in the background of almost our entire digital lives, yet it's notoriously wrapped up in heavy, intimidating jargon: machine learning. We're going to strip away the complex math and the confusing terminology to reveal how this tech actually works under the hood. My goal today is to show you that the foundational concepts powering the most advanced AI out there are incredibly logical, accessible, and, honestly, completely fascinating. Okay, let's dive into this. We've got a 5-part roadmap today. First, the machine learning paradigm, then the 3 flavors of learning, followed by the actual engine of learning, the data reality, and finally, the ethics and future impact of all this. Starting right off with part 1, the machine learning paradigm, moving from explicit rules to learned patterns. So to really wrap our heads around this shift, think about a super everyday problem. How exactly does your email inbox know what spam is? I mean, when an email hits your inbox, how does the computer instantly decide to just banish it to the junk folder instead of putting it front and center? Well, in the old-school traditional programming approach, a human developer had to sit down and write out explicit rules, what we call heuristics. You'd spend months typing out rules like, hey, if the email contains this specific word, mark it as spam. Or, if the sender is unknown and there are 3 exclamation marks, it's spam. But here's the problem. Spammers adapt. They start spelling things with a number 1 or hiding invisible text in the background, and suddenly your rigid rules are totally broken. It's basically like trying to hold water in a sieve. The system is incredibly brittle. And that brings us to the core paradigm shift. Instead of human programmers writing those brittle, easily broken rules, machine learning totally flips the script. We write a program, we feed it thousands of emails that are already labeled spam or not spam, and then we let the machine discover the complex mathematical relationships completely on its own. We stop giving the computer the rules, and instead we give it the data so it can write the rules for itself. So the crucial point here is this formal definition. Machine learning is basically a system that learns patterns from data without us having to explicitly program it with task-specific rules. It actually gets better through experience. It's not magic, guys. It's a profound shift in how we instruct computers to solve problems. Moving on to part 2, the 3 flavors of learning: supervised, unsupervised, and reinforcement. You see, machine learning isn't just one big monolithic thing. It comes in a few distinct flavors depending on the kind of feedback it gets. Think of supervised learning like a student doing math homework, but they have the answer key in the back of the book. You give the algorithm a data set with the inputs, like the words in an email, and the correct labels, like spam or not spam. It checks its work against that answer key. On the flip side, unsupervised learning, that's like being handed a massive mixed box of Legos with 0 instructions, no answer key. The data is entirely unlabeled. The algorithm's job is just to naturally find the hidden structures, grouping pieces by color or shape without anyone telling it what the right groups even are. Then we've got the 3rd flavor, which is reinforcement learning. Imagine you're teaching a dog a trick. You obviously don't micromanage its muscles, right? You just give it a treat, a reward when it does something good, and you say no, a penalty, when it does something bad. Over time, through good old trial and error, the agent figures out a strategy to maximize those rewards. And this brilliantly illustrates how these different paradigms tackle entirely different real-world problems. With labels and an answer key, supervised learning gives us spam filters and housing price predictions. Working with unlabeled data, unsupervised learning discovers hidden customer segments and weird anomalies. And with states, environments, and rewards, reinforcement learning is exactly how we're teaching robots to walk or getting AI to completely crush humans at chess. All right, part 3, the engine of learning. Let's look at how machines actually learn under the hood. Before a machine can learn anything, it has to know exactly how badly it's failing. That is the entire job of what we call a loss function. It just looks at the model's current guess, compares it to the true answer, and spits out a single number. The higher the number, the worse the prediction. The whole game of machine learning is literally just trying to make that loss number as tiny as possible. And to shrink that number, we use something called gradient descent. Now, I know gradient descent sounds super intimidating, but picture this. You are blindfolded on a very hilly landscape, and your goal is to find the lowest valley. Since you can't see, you just feel the slope of the ground with your feet, figure out which direction goes down the steepest, take a step, and try not to trip. Then you repeat the process. That's exactly what this algorithm does mathematically, feeling its way down to the lowest possible point of error. Put it all together and you get this incredibly elegant 4-step loop. The system makes a prediction. It calculates the loss to see how wrong that prediction was. It uses gradient descent to adjust its internal dials, its parameters, just a tiny bit downhill, and then it repeats, thousands or maybe millions of times. This simple, cyclical, logical loop is the mathematical engine powering literally every piece of machine learning tech out there today.
Next up, part 4, the data reality, the fuel and the challenge.
Now, what's really interesting here is that the most perfectly engineered mathematical engine in the world is completely useless without the right fuel. The absolute hard ceiling for any model is this: garbage in, garbage out. You could have the most advanced neural network on the planet, but if you feed it noisy, biased, or just plain incorrect data, your predictions are going to be completely useless. No algorithm can magically overcome bad data. Because of that reality, engineers have to do a massive amount of mandatory data prep. Remember, these mathematical engines only understand numbers, so we have to normalize the data, making sure a huge number like income in dollars doesn't mathematically overwhelm a smaller number like age in years. We have to encode categories, turning concepts like the color red or blue into ones and zeros. We use imputation to logically fill in the blanks when data is missing. We even artificially augment data, like slightly rotating pictures of cats, just to give the model more robust examples to learn from. But even if your data prep is absolutely flawless, you're still going to face the central challenge of machine learning: overfitting. Overfitting happens when a model learns the training data too perfectly. It's exactly like a student who just memorizes a practice test. Sure, they score 100% on the practice, but when they sit down for the real exam with slightly different questions, they completely bomb it because they memorize the quirks instead of actually learning the underlying concepts. Preventing this is a daily battle for engineers. And that brings us to our final section, Part 5, Ethics and Future Impact, the human element. As we pivot away from the math and look at the real-world consequences for humanity, we have to remember one crucial thing. Algorithms are not inherently objective. They're basically statistical mirrors. So, if we train a model on historical hiring data and that past data contains human discrimination, the model is going to faithfully learn to replicate and even amplify that exact same discrimination. It doesn't know right from wrong. It only knows the patterns in the data we provide. It learns our societal biases. So as we keep building these incredible engines to process the endless oceans of information we generate, they're really holding up a mirror to our history, our biases, and our behaviors. So what does this all mean? Well, the ultimate question isn't just what the machines are learning from the data, it's what that data reveals about us. Thanks for joining this explainer. Stay curious and keep learning.